All right. Good morning, everyone. Sige, shout out kay Chazel, David, Michael, John Christian, Jeanette, Raphael, and Ezekiel. Okay, so I'll start with this sort of motivational GIF that I found. Ano? So sa mga 155 pips din dyan, replay ito. Pero I just would like to share it with all of my classes this semester. So this is something that we oftentimes forget, or actually we just simply don't do it. All right. So that is celebrating little victories. So meron kasi mga bagay tayong ginagawa, especially yung mga daily chores, yung mga maliliit na bagay nating ginagawa day in and day out, we usually fail to appreciate them and celebrate these little victories. Okay? Halimbawa, nakatapos ka ng isang problem set. Yay! So, sa sobrang busy, all right, siguro ang nangyayari na lang after one problem set, you jump to another or to another homework or to study for another subject. But we fail to appreciate yung mga bagay na ginawa natin, lalo na itong mga maliliit na mga bagay. And I think we ought it to ourselves to give ourselves a pat in the back kapag ka meron tayong mga nagagawa, kahit mga maliliit na bagay, even though some persons will say what you did or what you accomplished is insignificant or it is just a little portion of the big task that you need to do. Pero ito mga maliliit na bagay na ito yung something na nag-add up into the successes that we will have in the future, right? And people will only see the final product, pero tayo mismo yung nakakakita ng mga maliliit na steps na ginagawa natin araw-araw. And we should celebrate these little victories because a little step is a step nonetheless. So kailangan nating i-celebrate yung mga bagay na yan. And doon nga sa 155 na-realize ko, oo nga, no, ang buhay parang integral. Kasi pag nag integrate ka, you're integrating, say, dx over your finite lifespan. So, halimbawa, from 0 at your birth to, say, whatever age you are now. Kunwari, 25 years old tayong lahat ngayon. All right? Feeling 25. Pag in-integrate mo yan, makakuha ka ng isang value, right? Anong value na? 25 nga ba? All right, 25, right? So this sums up to 25. But what are we putting into the integral? What we're putting here would be dx, and dx are infinitesimal quantities. Yan yung haba ng mga rectangles na super liliit that we made them approach zero. So these are infinitesimal widths. So wala nga sila, yung width nila ay close to zero, very, very close to zero. And yet, these little amounts, when accumulated and when compressed, will give us a finite value. And oftentimes, may mga function nga pag in-integrate natin, infinite yung sagot. So these little things add up, all right? And these contribute to the final version of ourselves. So yun lang yung gusto kong sabihin, especially we're on the reading break right now, on the brink of the reading break. So try to celebrate these little victories. Yung mga nagawa nyo in the past few weeks, they are not easy, especially with our current setup. So give yourselves a pat in the back. You deserve it. At saka magandang gawing habit ito, yung pag-reward sa sarili with the little victories. Kasi excuse nyo yan para ma-pamper yung sarili nyo. Ginagawa ko yan. Pag nakapag-check ako ng isang problem set, okay, pwede akong mag-binge watch or pwede akong hindi magtrabaho ng weekend, pwede akong mag-order sa online shopping app, pwede akong pumunta sa coffee shop, and so on. So excuse ko na yan para i-treat yung sarili ko. But actually, on a more profound note, this celebration of little victories, I think, is one motivational spark para sa atin to keep moving forward. So because you need to have a sense of accomplishment, and I hope you guys will find such a sense, all right, of fulfillment or accomplishment kahit dun sa mga maliliit na bagay na nagagawa nyo, because these are the things that can drive you to move forward. Okay. So that's it for my initial segment for today. So back to regular programming na tayo. Hold on, guys. Hindi na nawala yung yung runny nose ko, yung allergy ko kapag ka nagka-klase. But anyway, so that's it. And then as I've said, we are on the brink of the reading break. So I hope masaya na kayo, makapagpahinga tayo sa mga susunod na linggo. After the reading break, we have the Holy Week. Pero panira yung Lab Exer 2.2 so we will go back on Holy Monday in the labs to do laboratory exercise 2.2. I'll have the questions for that lab excerpt probably on Monday. Okay, para masimulan nyo na. You can do it during the reading break, or you can take your reading break as a total break, as you should or as you deserve. So pwedeng gawin nyo na lang siya sa Monday, April 11. And then I will give you April 13 as an additional holiday. So we will not meet in the lecture on the 13th. So ang susunod na nating lecture session will be on April 20th. Tama ba? April 20th? Super tagal pala, no? Parang uno pa lang ngayon ng Abril, tapos 20 na tayo uli magkikita-kita in the lecture. Pero D2L, I'll see you on, hopefully on April 11. Okay? Tapos, hindi ko natapos yung temporary module 6 that I uploaded last time. And there's just a little amount of material left, all right? But dahil yun nga, April 20 na yung susunod na lecture, I don't want to start a brand new lecture, especially it's about LU factorization, which is medyo involved. Tapos napaka-awkward na mahati siya dun sa gitna. So I decided I'll just finish the temporary module number 6 today. And then when we go back on the 20th, we're going to start LU factorization. Probably it will take the whole lecture, or even it will spill over the Thursday lecture for that week. Pero let's see. Pero hindi na ako mag-introduce ng panibagong topic for this week. Tapusin lang natin yung Gaussian elimination. Now, last time we reviewed how you solve systems of linear equations, especially in your elementary algebra classes, wherein meron tayong equation, tapos we look for a appropriate multiplier to one or two of the rows, okay? Tapos you carry out the multiplication, then you add one row to another, or as a scalar multiple of a row to another scalar multiple of another row. And we do that to the end of decreasing the number of the variables. So if you have a 2x2 matrix, you're going to start a 2x2 system. You're going to start by looking for appropriate multipliers so that one of the variables will be gone. Tapos pag isa na lang yung variable, okay ka na, masosolve mo na yung value niya. And then you just do back substitution. You go back to an equation that has two unknowns. You plug in the value of the variable we found from the previous step, and then you'll get the other solution, right? Ganun din sa 3x3. Pag meron kang 3 equation of 3 unknowns, okay, kukunin mo, bubuo ka ng dalawang pares. Tapos sa dalawang magkaibang pares na yun ng equations, mag-eliminate ka ng isang variable. So down from 3 unknowns, you will have 2 equations with 2 unknowns na lamang. And then yung natirang dalawang equations na yun, siya naman yung pagsasamahin mo para ma-eliminate yung isang variable. So you're down to a single variable equation. It is linear, so madali siyang i-solve, okay? So, ganun yung nangyari, back substitution. So, alam mo na isang variable, hanap ka ng equation na may dalawang variables, you plug in the value of the previous variable, then magkakaroon ka na ng two solved variables. Pupunta ka ngayon sa isang equation na may tatlong unknowns. Ipa-plug in mo ngayon yung dalawang solved variables para makuha naman yung natitirang equation. Okay? So essentially, that's what we did, but we used matrices in order to express those operations involved. Ang ginawa natin last time ay yung Gaussian elimination, and we performed this elimination process by using matrices, specifically elementary row operations on matrices. Okay, so and then nakuha natin yung eksaktong sagot last time. I'm not sure if we checked if really this vector of solution, or this solution vector 0, 1, -1, 0 solves the system exactly, but you can check it for yourselves. You plug in this to x1, to x2, to x3, and to x4 in our original system, and then you'll get the final answer. Okay, excuse me. Mali yung sinabi kong final answer. Sorry, nagmamadali ako para asikasuhin ang aking nag-aalborotong ilong uli. Alright? So, ipa-plug-in mo siya dun sa original equation para makita kung totoo ba, kung eksakto ba yung solution, if we will get the right-hand side of our equations. Alright? Now, this is another lesson that I want you to get from the previous problem set, because I saw some of you perform dun sa isang problem, hindi pala problem set, dun sa isang lab exer. Okay? Lalo na dun sa may deflation method, right? So yung iba, okay, nakuha nila yung first step no, okay. Nag-perform sila ng halimbawa Bairstow's o kaya Mueller's dun sa isang polynomial equation, right? Tapos okay, may nakuha silang solution. Tapos gumawa sila ng tapos nag-deflation kayo, right? So bumaba na yung degree ng polynomial. Tapos ang ginawa nila ay okay, hindi nila na-realize na mali yung nakuha nilang solution or root mula dan sa unang run ni Bairstow. So, unang run ni Mueller. So, ibig sabihin, mali na yung deflated equation. Sorry, I'm all over the place, but I just remembered, okay? So, halimbawa, meron kang polynomial P. Tapos, nag-Mueller's ka, kunwari. Tapos, si Mueller's, binigyan ka ng R1 star, okay? Tapos yung R1 star, ang alam natin, ayan yung gagamitin natin sa deflation, alright? Para mapababa yung degree ng polynomial P. So ideally, what you'll do is to divide P by X minus R1 star, and then you will run Mueller's again on the deflated polynomial, alright? However, this process or the accuracy of the entire process hinges on the previous values of the R1 stars, alright? So, parang chain yan. Pag namali ka sa R1 star, automatically mali ka na dun sa mga natitirang parts ng solution. Okay? Now, merong mga instances na, okay, for whatever reasons, okay, polynomial, nag-Mueller's, maganda yung R1 star na nakuha nung iba sa inyo, right? And that's fine. Okay, you'll get perfect credit for the first step. But when they did the deflation for whatever reasons, nagkamali yung division ng P over X minus R1 star. So kung mali yung P minus R, yung P over X minus R1 star, so halimbawa ito ay suspect. So suspect yung value niyan. Alright? So tapos dito ka mag-Mueller's ulit. May makukuha kang R2 star. Okay? So ito, mali na tong R2 star mo rin. So, mag-chain reaction na yan pababa dun sa solution. Now, some of you didn't catch na mali na pala yung R2 star nilang nakuha. Kasi di ba may check tayong ginagawa every after iteration, nagpla-plug in tayo dun sa polynomial para makita kung close enough nga ba to 0 yung nakuha nating solution. Alright? So, ang ginagawa nating isang check, okay, let's compute. So, para ma-check to, kino-compute natin yung f of R1 star. And let's check if that is close to 0 as desired. Sorry, it should be P. Okay? So, pina-plugin natin. Yung iba, okay, ginawa nga yung checking step na to para nga naman ma-ensure na bawat step nung chain na to ay nag-work properly. Okay? So, that's fine. Alright? Tapos, dito nga sila nagkamali. Pero ang sister ay, meron silang R2 star na nakuha, pinlog in nila ito dun sa suspect na expression para dun sa deflated polynomial. And of course, if instead of P over X1 star, ang na-compute mo ay defective na polynomial, halimbawa na-compute mo halimbawa ay si Q, instead of P over X minus R1 star, tapos kay Q ka nagpa-Mueller's, so expectedly, kung tama yung program kay Mueller's, yung Q of R2 star ay magiging close to 0. Okay? Pero what you got is R2 star, which is an approximate to a root of Q and not to the actual deflated polynomial P over X minus R1 star. So nakita niyo yung medyo problema rito. Hindi nag-work yung sanity check na ginagawa natin every step kasi doon ka nag-plug in sa defective na polynomial. So it is always better to do the checking on something that you know is correct or is exact. Huwag kayong mag-checking process or huwag kayong magsa-sanity check using a value that you also solved. So kung may pagkakataon kayo, meron kayong alam na mula sa problem o given facts, yun yung gamitin nyo sa sanity check. Iwasan yung gamitin yung mga previous yung na-compute para dun sa sanity check. Alright? Remember, we are computing for approximates of R1, R2, R3, and R4, which are the roots of a, say, quadric polynomial P. Okay? So, ibig sabihin, si R2 star ay approximate para sa root ni P. It would have been better if you plug in R2 star into P. Kasi kung close siya to 0, then yeah, I'm good. R2 star is a good approximate. So that means most likely tama yung deflation process. Pero kapag yung R2 star, pinlog in mo kay P, tapos hindi siya close to 0, that means something is wrong in the process. And you will be able to trace back the mistake into the deflation process. Machi-check mo ngayon at yun na, okay, parang mali yung synthetic division ng P over X minus R1 star. And you will be able to debug or to rewrite your code. Okay? So yun lang yung gusto kong sabihin dito, right? So kapag ka mag-checking kayo or magsa-sanity check, gawin nyo siya sa isang bagay na alam nyo for certain at hindi yung mga na-compute nyo o mga na-derive nyo na values. Okay? So this would be a real nice lesson, especially if you're building a large code, right? So pag malaki na yung ginagawa yung program, mahirap i-debug yan line by line. So probably every step of the way, do a sanity check and see kung nag-work nga ba as expected yung program nyo. Pero ang gagamitin nyo sa sanity check ay yung something na alam nyo for a fact. All right? Okay, so going back, balikan natin yung ginawa nating process dahil marami naman tayong oras, pero inubos ko na siya sa kakakwento. Ano? So balikan natin, mag-consider tayo ng isa pang example ng Gaussian elimination. So consider, okay, I entitled the example Gaussian elimination in a finite machine. Okay, tingnan natin ano yung nagiging epekto ng paggamit ng isang computer sa pagko-compute sa Gaussian elimination. Because this will reveal something that is reveal that is something significant insofar as the accuracy of results from a computer is. Kasi kapag ginawa natin siya by hand, wala tayong nagiging problema. Alam natin that the solution, that the process will work, okay? Especially if non-singular yung matrix kasi makukuha natin yung unique solution promised by theorem 6.1. Pero ang problema, hindi naman natin to gagawin by hand lagi, right? Level up na tayo kasi hindi na tayo nasa elementary. So, pwede na tayo mag-calculator o mag-computer pag solve ng linear systems, right? And especially if you're doing modeling or you are doing dynamical analysis of, say, natural phenomena, yung matrix mo, yung variables mo might stand for different variables. Tapos sa tunay na buhay, maraming mga variables ang involved sa isang process, right? For instance, nagmo-model ka ng epidemic curve. So nandyan yung potency nung dapat variable mo yung potency ng virus, yung transmission rate, yung hospitalization rate, vaccination rate, survival rate, and so on. So napakaraming variables ang involved. So and it will not be practical to perform everything by hand. So we will resort to using computers. Okay. So tingnan natin siya sa malit na example dito, 3 by 3, example 7, okay? Now, the first example asks us to do the Gaussian elimination exactly. And then what we'll do next is, after doing that, makukuha natin yung exact solution. We will perform the Gaussian elimination, but this time in a primitive 4-digit rounding arithmetic. Of course, this is a very silly example kasi mga computers natin, hindi lang 4-digit yung kaya nilang i-compute. Siguro nung panahon na ano ba yung mga sinuunang computers. So siguro nung mga panahon yon, pwede pa yung 4-digit arithmetic, right? So pero ngayon we can work with say double precision, 16 or 32 digits, 16 or 32 significant digits in our desktop computers or even more, all right? So kaya hindi to magiging problema, pero pag malaki na yung system, tapos yung matrix natin ay magiging ill-conditioned pa, this will be a big problem, right? But just for sake of illustration, gawin natin siya dito sa 4-digit rounding arithmetic, okay? So pero una, para meron tayong baseline, a result, gawin natin yung Gaussian elimination sa isa exactly. Manu-manuhin natin ito. So we'll work with fractions. So what I did here is take the coefficient matrix, kinuha ko lang yung proper yung coefficients ng equation in the proper order, okay? And then line them up into a rectangular array. And rectangular arrays are simply matrices, right? And then I'll augment to the coefficient matrix the vector of constants. Yung mga right-hand side, idikit ko dun sa coefficient matrix. And then I will use elementary row operations to reduce the augmented matrix into an upper triangular matrix appended by a constant vector. Okay? Remember, gusto natin upper triangular yung nandito para magawa natin yung back substitution. Okay? Now, ano nga ba yung ginagawa natin? We pivot. Ang ginawa natin last time, we pivot on the first row. Okay? Specifically on the first element here. Okay? Nag-pivot ako sa first row, hindi magagalaw yung first row, carried over siya dyan. And then remember, our goal is for this matrix to be reduced to an upper triangular matrix. So we want everything below the main diagonal to be equal to 0. Okay? So ang gagawin natin ngayon, ano dapat yung i-multiply ko kay 1/3, ano dapat yung i-multiply ko kay 2/3 para pag inad ko yung scalar multiple na yon kay 1/3, ang sagot ay 0. Kasi gusto ko yung entry rito dahil nasa ilalim yun ng main diagonal ay mag-0. So I'll just solve the system, 2/3 times something. Okay, let's call the something S. Halimbawa, ito dapat ay equal kay negative 1/3. Kasi si negative 1/3 yung additive inverse ni 1/3. So here we'll get S equals negative 1/3 times 3/2. So I'll just need to multiply it by negative 1/2. And that's what I did. I multiplied the first row by the pivot row, the first row, by negative 1/2 and add the result to R2. Okay, mag-0 ito, and then I'm lucky that this became 0 as well. Okay, tapos ito ay magiging negative 3/5, negative 3/5. So basically here, if you're thinking of writing a program, you can just say, okay, madali lang pala to. Kasi pag nag-pivot ako, pwede kong gawing multiplier dun sa unang step ay kung ano man yung entry. So, ano yung multiplier natin dapat? Dapat siya ay negative nung entry sa A21 times reciprocal ng entry sa A11. Okay? And then you can deduce the pattern para ano yung multipliers para dun sa first row para ma-zero mo yung yung first entry, yung leading entry ng second row at saka third row. Okay? Now, that's the same thing. I did the same. I used an analogous formula to see that I need to multiply the first row by negative 3/10 para pag yung 2/3 times negative 3/10 ay inad ko sa 1/5, ang sagot ay 0. Kasi yun nga yung goal natin. We are pivoting on the first row and wanting to make the first column to be in the right form. Ihanda natin siya para maging upper triangular na siya. Okay? So our first application of the elementary row operations, dalawa yung in-apply ko actually, gave us this augmented matrix here. Tapos we will pivot on the, we will move on with the elimination process. Supposedly, we will pivot around the second row. But unfortunately, 0 na itong nandito sa diagonal na yan, right? And hindi mag-work yung multiplication process natin because I cannot multiply, I cannot find anything that when multiplied to 0 will give me positive 36/70, right? Kasi di ba yung pivot element, siya yung pinandi-divide natin. Reciprocal niya, yung pinang-multiply natin. Tama ka ba? Reciprocal niya. Yeah, I need its reciprocal to find what is to be added to itself, right? At what is to be multiplied to itself para ma-cancel yung nasa ilalim niya. So the idea here is I cannot find any real number to be multiplied on the second row para mag-vanish yung negative 36/70. Because the only way to do so is that a multiple of this entry dapat maging yung multiple ng entry na to dapat maging 36/70 pero 0 na nga siya. Hindi ko naman pwedeng gamitin ito kasi pagka nag-multiply ako nito or nag-multiply ako rito, in-add ko sa third row, most likely ito magiging non-zero na kasi meron siyang 2/3 dyan. But so that means this is inappropriate for a pivot element kasi nag-0 na yung kanyang leading entry rito. So instead, we will do interchange of rows, which is a valid elementary row operation. So I will interchange the second row and the third row to get this one. And luckily for us, that simple interchange gave us an upper triangular matrix na. Ito kasi yung main diagonal. Lahat ng nasa ilalim ng main diagonal ay 0 na, so we are good. Alright? Now, paano natin makukuha yung solution? Back substitution. Why back substitution? Kasi magsisimula ako dun sa ilalim ng matrix. Kasi yun yung merong isang unknown lamang, tapos meron kang right-hand side. So you will get one equation with one unknown. Okay? Why? Because the thing here is, mamumultiply itong matrix, itong bagong coefficient matrix by the unknowns, right? So when you multiply 0, 0, negative 3/5 by the vector of unknowns x1, x2, and x3, we will get negative 3/5 x3, right? Remember kung paano nagmo-multiply ng matrices, okay? And then equal siya dun sa right-hand side value, dun sa augmented portion ng matrix. So this is equal to negative, this is equal to negative 3/5. Solve for x3, we're going to get x3 equals 1. There we go. And then when we do back substitution, so ito naman yung gagawin ko. Multiply ko naman yung second row dun sa vector of unknowns. 0, negative 36 over 70, 17 over 50. Multiply with this guy will give us what? Will give us negative 36 over 70 x1 plus 17 over 50 x3 equals, x2 pala yun, equals negative 163 over 50, okay? And then you plug in the value for x3 that we computed. We know that x3 is equal to 1. So we will get this equation, which involves only the variable x2. And then since this is linear, madaling mag-solve ng solution yan. Of course, except fractional yung involved, so medyo mahirap mag-add or subtract ng fractions. But if you do so, you'll get 7. And then you'll do the same thing, but now work with the last equation or with the topmost equation. There would be initially 3 unknowns, but we already knew that x2 is equal to 7 and x1 is equal to 3. So we can compute for x1. And doing so will reveal that x1 is equal to 1. So yung vector C, consisting of 1, 7, and 1 is the exact solution vector. And how do we check our solution? Kung medyo paranoid ka na, ayaw mo nang mabawasan yung scores mo sa LabXer, plug in mo lang yung 171 doon sa tatlong original equations. So whenever you get the chance, doon ka laging mag-plug in sa given. Huwag doon sa derived equation. Kasi supposedly, pwede mo yung i-plug in dito, kaya lang kulang yung information, right? At saka, wag mong pagtiwalaan ito kasi nga sanity check ito dun sa process na kinary out mo. So, do not use the results of the process to check if the process is working as expected. So, I'm going to plug this in into one of the original equations dito and see if I'll get the right-hand side. Okay? So, ganun yung pag-check. All right, so nothing different there. Basically, it's just a review of what we did last time. Okay, Gaussian elimination. Pero ngayon, tingnan natin ano yung mangyayari kung gagawin natin siya sa isang 4-digit rounding arithmetic, which is basically what happens in a computer, except that you might be working with more than 4 decimal digits. Okay? Pero on a primitive computer, gawin natin siya mano-mano. Let's pretend na tayo ay mga computers. So una kong gagawin ay ita-translate ko yung mga fractions, okay, doon sa coefficient matrix papunta sa 4-digit decimals, right? So dito, so yung 2/3, kita nyo kagad yung pagbabago. Yung 2/3, 0.6667 na siya doon sa machine, doon sa point of view ng machine natin. Pero in reality, siya dapat ay 0.6 bar, okay? So the 4-digit rounding arithmetic, basically, may inherent na siya na error na order big O of 10 to the negative 4 at the least. All right? Or yung relative error niya ay 10 to the negative 4 na. Or a multiple of it, right? So we expect na if everything goes well, ang error din natin is around of order 10 to the minus 4 din. Kasi yun yung sinacrifice natin in the machine implementation, right? 4 digits lang yung ginagamit natin. So basically, we're expecting an error of order 10 to the minus 4 due to rounding and due to the arithmetic, right? And if everything is well, then dun sa final answer natin, yung mga relative errors coming from, compared to the actual values that we got from part A should be of order 10 to the minus 4 as well. If we get something beyond that or something very far from that, then we can say something is wrong and something should be done. And that's where numerical analysts o yung mga work on approximation theory will come in. Paano ma-improve yung Gaussian elimination from the point of view of a machine. And hopefully here you see kung saan pumapasok talaga yung mga mathematicians, right? So you might think na dapat ang numerical analysis ay comsci kasi puro programming naman yung pinapagawa ni Sir eh. Pero tayo as mathematicians, we're going beyond programming, all right? So we don't deal too much with the hardware, paano ma-accelerate yung method, pag-upgrade nung components ng computing machine. Pero ang wino-work kasi pang-comsa yon, sila or computer engineers yon. Sila yung bahala paano natin gagamitin yung GPU graphics, hindi lang sa pagdodota, pero pati rin sa pagko-compute using parallel computing, ano? So pero tayo, ang ginagawa natin ay, sige, wala tayong alam sa hardware, so humanap tayo ng paraan kung paano maging mas efficient yung process na ipapagawa natin dun sa mga computers. Alright? So yun yung pinagkaiba ng numerical analysis from simple programming. Okay? Now, sige, tingnan natin. Baka naman walang problema, baka paranoid lang tayo. Sige. Oh, by the way, yung 4-digit round, sige, later na lang yan. So, augmented matrix, okay? Okay, nakita ko na pala siya. Look at this one, 2.867. Yung sa example na to ay strict pala yung 4-digit rounding arithmetic. So, kasi yung una ay 43/15, pero tinruncate yan ng machine, ginawa siyang 2.867. Kasi nga strict siya na 4 digits lamang yung gagamitin niya at every step of the way. Alright? Meron lang yung multiplier dun sa floating point representation na 10 to the 0. Pag lumampas na ng 4 digits, halimbawa meron ka ng 15,000, okay? Babasahin pa rin niya ni machine, pero ang basa niya ni machine dito ay 1.500 times 10 to the what? 1, 2, 3, 4. Times 10 to the 4th. Tapos i-store niya na lang itong multiplier na 10 to the 4th. Pero in every calculation, ang gagamitin niya ay 1.500. Okay? So kaya dito makikita nyo, talagang strict na 4 na digits lang yung ginagamit. Which is typical. This is what really happens in a machine kasi kino-convert natin yan sa floating point representation niya. Okay, so let's do the first pass of the elimination process. Gawin natin siya dito. Alright. Nag-pivot uli ako sa first. Oops, sorry. Nag-pivot uli ako sa first row. Okay. Nag-zero itong mga to. But at every operation, I do 4-digit rounding. Okay. So, alam ko ang pang-eliminate dito ay what? Negative 0.3333 over 0.6667, right? So here, this was multiplied by 0.3333 negative over 0.6667 para makuha ko yung pang-cancel para mag-zero ito. Alright? But when I calculated this, nag 4-digit rounding arithmetic ako. Alright? So that means the result here suffered from the round-off error that was incurred in solving for the multiplier. Okay? So, yan. So, magpa-propagate na dyan yung error. So, kaya makikita nyo to, 0.0001. Pero dun sa exact solution natin kanina, eksaktong nag-zero rin yan. So, we see a little variation here, but we are not worried too much because this is within 4 decimal digits or 3 decimal digits from what we expected from the actual result. Hindi naman to nalalayo dun sa zero na meron tayo mula dun sa previous solution. So everything seems fine so far. And then let's do another pass of the elimination procedure. Ngayon naman, ito na yung gusto kong i-eliminate. So ito yung makukuha ko. Tapos dito, pwede na ako mag-back substitution. Okay? So I'll have negative 3086 x3 equals negative 3087. 4-digit rounding arithmetic will tell me, okay, it's 1.000. And then I'll do 0.0001 x2 minus 0.06 x3 equals negative 0.5997. I'm going to get 3. And then last thing, I'm going to get 2.715. So ito yung solution natin using a 4-digit rounding arithmetic. But this is a little bit of a shock to us, all right? Bakit? Kasi ang layo nito sobra doon sa exact solution. Okay? The error in E3, the error in X3 is not that, it's actually not, actually is equal to 0, right? So 0% yung error. Pero kay E2, 57.14% na yung error. Ang na-compute natin sa 4-digit rounding arithmetic ay 3. Pero alam natin yung exact solution ay 7. So this is 57.14% error. And this will propagate into X1. Kasi para ma-compute si X1, gagamitin ko yung value ni X2 at saka ni X3. Si X2 meron ng 57% error, so I expect X1 to suffer too much. And actually, it suffered threefold. Yung error niya na is around 171.5%, which is huge, knowing that we are using a 4-digit rounding arithmetic. So we are expecting an error of around big O of 10 to the minus 4 or at most big O of 10 to the minus 3. Pero ito ay what? Ito ay 10 to the second power. Ito ay 10 to the negative 1. So napakalaki ng order of magnitude ng relative error. Okay? So that's a problem. And we want to see paano natin masusolusyonan to. Or is there really a remedy to it, or we'll just give up and say, bawal na ang Gaussian elimination sa computers na mababa yung precision? Of course, we are persistent. We are mathematicians. So we need to get to the bottom of this and try to remedy the problem. Okay? Now, part of designing a way in order to remedy a problem is to know the problem itself. All right? So kailangan malaman natin saan to nangyayari. Okay. So the problem here is nagkaroon ng cancellation error. Tingnan ko kung maalala ko kung saan siya nangyari. Okay, I think that happened here. Dito sa pagkuha ng result na to. Because here in the elimination pass, let's see. May ginawa akong subtraction of very small numbers. 2.87. Let me see if I can trace that back. Nakalimutan ko kung saan nangyari yung cancellation error. Let me just do the calculations quickly. Blah, blah, blah. Hold on, guys. Okay, I think one of the reasons that contributed to the erroneous solutions is the fact that here, the multiplier we used here was basically, para makuha ito, para mapa-zero ito, involved the division by a very small number, all right? Because again, to find the multiplier to this guy, para maging zero ito, kailangan natin kunin yung 0.5143 over 0.0001. Okay? So ibig sabihin, we divided by a very small number. And that might have caused the problems. And then dun sa arithmetic, meron siyang, hindi ko ma-pinpoint kung saan nangyari, pero meron siyang nag-subtract tayo ng dalawang numbers na napaka-close sa isa't isa. And you know, if two numbers are very close to each other, so close na up to 4 decimal digits sila ay parehas, yung difference nila ay iti-take ng machine to be equal to 0. All right? So, halimbawa, supposedly magsasubtract ka ng number na to, saka ito. Okay? So, non-zero yung magiging difference nila. Pero sa 4-digit rounding arithmetic, buburahin to ni computer, Buburahin niya ni computer kasi hindi siya designed to work with more than 4 decimal digits, so the difference will be taken to be 0 right away. So merong isang instance dito, hindi ko lang matandaan kung saan nangyari, pero nagkaroon ng cancellation error. So those are two things that we want to avoid: cancellation error and division by a very small number, because that would be from the perspective of a finite machine an unstable operation. Okay? So ano yung solution? Well, meron tayong i-introduce na pivoting technique, right? So kasi so far, ang Gaussian elimination natin, nag-work tayo dun sa given matrix, dun sa order ng given matrix, alright? Pero tingnan natin ano yung pivoting strategy. Meron dalawang pivoting strategy ako nilagay dito, right? Yung una ay partial pivoting, yung pangalawa ay scaled pivoting, alright? So partial pivoting, okay, hindi natin iti-take yung, hindi natin gagawin yung Gaussian elimination is necessarily in the same order as the problem was given, pero magpipivot tayo dun sa row na may pinakamalaking leading entry. Alright? Hindi ko siya basta-basta ipe-perform right away. So tingnan natin, balikan natin yung example kanina. Marami akong sinabi dyan, may description yung method, pero dahil paubos na yung oras, alright, na hindi ko pa rin natapos, ang daldal ko kasi. So, papakita ko na lang yung method, tapos pwede nyo balikan, basahan yung notes na nilagay ko dyan. Okay, so tingnan natin yung example uli. Yung same example, 4-digit rounding arithmetic pa rin, pero gamitan natin siya ng partial pivoting. Okay? So sa partial pivoting, at every pass of the elimination, titingnan mo ngayon yung, pipili tayo kung kanino tayo magpipivot. Magpipivot tayo dun sa row na may leading entry na may pinakamalaking magnitude. Okay? So on the first pass of the algorithm, all of them will be candidates para maging pivot. Kasi hindi pa tayo nakakapag-decide kung sino yung magiging top row. Okay? So yung top row na yun, siya na yung magiging pivot. Right? So ang requirements sa partial pivoting, punta ka ngayon sa first column. Tingnan mo sa kanila kung sino yung may pinakamalaking magnitude. Right? Ang may pinakamalaking magnitude sa mga entries sa first row ay yung 0.6667. So that means we will pivot around the first row. So si first row, i-maintain ko siya to be the first row of the upper triangular matrix U. Okay? Tapos I will perform the usual elimination pass. Ito yung makukuha natin, which is exactly the same matrix that we got from the first pass nung algorithm run kanina, dun sa without pivoting. So nothing has changed. Pero when we go to the second elimination pass, kailangan na natin kalimutan yung first row. Hindi na tayo magpipivot sa first row kasi settled na siya dun sa top. Alright? So ngayon, ang maglalaban na lamang para maging pivot sa second pass ay yung second row at saka yung third column. Alright? And then again, we choose the pivot depending on the magnitude ng leading entries. So titingnan ko ngayon sa second pass, titingin ako sa second column. Tapos titingnan ko yung entries mula sa second row hanggang dun sa ilalim. Sino yung may pinakamalaking magnitude? In this particular case, this guy has the biggest magnitude. Right? So that means we should pivot around the third row. So ibig sabihin, ito dapat yung susunod. Dapat mapalipat siya ron. So dito ako magpipivot, so siya na yung magiging second row nung augmented matrix. Gusto natin maging upper triangular matrix. So we will do an elementary row operation. We will interchange the second and the third row. So pag in-interchange natin yan, ito yung makukuha natin. Okay? Tapos, then Gaussian elimination, the usual thing. And then we will get this guy. Okay? And then when you do the back substitution, kasi upper triangular na yan, main diagonal, puro 0 na yung nasa ilalim, upper triangular. We can do back substitution now. And look at what we got. 1.001, 7, and 1. Almost exact solution. Nagka-problema lang dun sa dulo. Pero it's not that bad because if we compute the relative error, that is just 0.1%. Or 10 to the negative 3, which is close to the order that we expected because the round of error is of order 10 to the minus 4 or 10 to the minus 3. Error is 10 to the minus 3. So we're quite satisfied with our result. Okay. And then you see the tremendous increase in the accuracy from an error of 157% and 57% for X1 and X2 respectively. It is now down to 0.1% and 0 respectively. Okay? So napaka-liit na bagay nung ginawa natin pero ang nangyari ron, na-avoid natin yung division by a very small number. Because in getting the right scalar multiplier dun sa without pivoting, we needed to divide something by 0.0001. But in this case, we are choosing yung divisor natin para dun sa scaling constant to be the largest one. Okay? So that eliminated the division by a very small number, leading to a much better result. Okay? Sorry, mangungutang uli ako ng mga 5 minutes uli. That pala, hindi na ako dumaldal nung simula. Alright? Para matapos natin hanggang scale pivoting. Alright? So yung pangalawa naman ay scale pivoting. Isa lang siyang variant ng partial pivoting. Pero this time, hindi lang natin i-compare, alright? Hindi lang natin i-compare yung magnitude nung nandun sa leading entries, pero ang i-compare natin ay yung scaled leading entries. In what sense, dapat titingnan natin yung magnitude relative to the fellow members in the particular row. Okay? So kasi posibleng, okay, ito yung pinakamalaki, pero super liliit naman pala ng mga nandito. Alright? So parang pag may discrepancy doon sa orders ng mga nandun sa rows na yon. Alright? So titingnan natin, parang madaya ito. Malalaki kasi yung kasama niya, so expected na malaki siya. Alright? Pero posibleng ito ay maliit, pero maliliit naman yung mga kasama niya. So this guy is large relative to its members or its fellow or relative to its row mates. Tapos ito, posibleng maliit siya relative dun sa kanyang mga row mates. Okay? Kaya yun yung tinatawag na scaled pivoting. Instead of merely comparing the leading entries, ang i-compare natin ay yung leading entries relative to their fellow members in the row. Right? Tapos meron pa ako ditong isang in-introduce na bagay, yung tawag natin dito, siya yung row tracker. Kasi sa machines, parang ang hirap na nag-i-interchange pa tayo ng row every step of the way. Right? Kasi nangyayari doon ay kumakain pa siya ng memory. Pag nag-interchange ka ng row, lalo na kung malaki yung matrix, yung current row, kailangan mo munang i-save sa isang variable, tapos actually yung dalawa, yung pagpapalitin mo, kailangan mo siyang i-save sa dalawang dummy variables, tapos saka mo pa siya i-assign. So mahirap yung assignment, lalo na pag napakalaki ng matrix. I don't know if you have encountered na nagreklamo na yung inyong computer na sobrang naubos na yung memory niya sa laki ng matrix. Kasi I encountered that before. I'm performing some simulations. Tapos parang 300,000 by 300,000 by around 2,000 yung matrix na ginagawa ko. Tapos I'm using my old computer na nagreklamo na siya, hindi na raw kaya nung RAM yung ganung kalaking matrix. So pag borderline ng ganung kalaki yung matrix, yung interchange ng row na mag-i-introduce ka pa ng dalawang dummy variables might not be efficient because you will eat up your RAM or your memory dun sa computer mo. Alright? So magkakaproblema ka na. So instead of pagpalitin pa sila, itatrack ko na lamang kung nasa na yung ano na yung ordering ng mga rows. Alright? So yun yung gagawin ko rito sa scale pivoting. Okay. So paano natin siya gagawin? Now we will compute the scale sa bawat row. Meaning, kukunin ko lamang yung maximum absolute value sa bawat row. Tapos ipapang-divide ko siya dun sa leading entry. Tapos ang pagko-comparein ko ay yung ratio ng leading entry with the scale S sa bawat row. Right? So parang percentages yung pinagko-compare ko rito. So para makuha yung mga SI, kukunin natin ano yung may pinakamalaking magnitude sa bawat row. Siya yung scaling constant o siya yung scale sa bawat row. Tapos para malaman ko kung sino yung pivot, ang gagawin ko ay yung candidate para maging pivot entry, alright? So, ibig sabihin, ito yung leading entry dun sa isang row, i-divide ko siya by the scale for that row. Tapos yung ratios, sila yung pagko-comparein ko para mapakita o para malaman kung kanino tayo magpipivot. Okay? Now, example. Iba na to dun sa system kanina. I have a brand new system, and as part of the exercises, in-update ko yung copy kanina ng module 6. Nagdagdag ako ng exercises, all right? One of the exercises there is for you to try solving this using partial pivoting and solve this exactly, and then compare the results with what I'll get here in the scaled pivoting. So para ma-compare nyo na, okay, meron ngang additional na nabibigay yung scaled pivoting. Okay? Now, how do we do this? Hopefully, I'll finish it in 4 or 6 minutes. Kukunin ko muna yung row tracker. Ito yung nagsasabi ano yung order ngayon nung current matrix relative to the original matrix A. Right? So, kinuha yung coefficient matrix. Dahil wala pa naman akong row interchange na ginagawa, so ang first row pa rin ay yung first row, second row pa rin ay second row, third row pa rin ay third row, fourth row pa rin ay fourth row. Okay, so yan yung simula lagi, 1, 2, 3, 4. Tapos kukunin ko yung scale ng bawat row. Okay? Oh, by the way, hindi kasama yung right-hand side sa paghahanap ng scale. The formula for S, maximum lamang ng entries ng coefficient matrix. It doesn't matter if you have a very large or a very small right-hand side. Okay? Kasi hindi naman siya kasama dun sa pagdedetermine ng upper triangular matrix. Okay? All right, so look at the first row. The coefficient matrix, yung maximum value ay nangyayari sa 4. So the scale for the first matrix, for the first row is 4. The scale for the second row is 2. Okay. The scale for the third row is 14, and the scale for the fourth row is 4. Okay. So yung T pala dito, ibig sabihin transpose kasi dapat sila ay column vectors. So ito yan, dapat. Tapos ito dapat ay 4, 2, 14, 4. Okay. Pero kasi ang pangit na isulat siya in a vertical form, sayang yung space. So lagyan ko na lang siya ng transpose dyan. Okay. First pass. So sa first pass, titingnan ko ngayon kanino ako magpipivot. But instead of simply comparing these two guys, because if I don't know the scales, kung partial pivoting lang yung gagawin ko, dito ako sa third row magpipivot. Kasi yun yung may pinakamalaking leading entry. Alright? Pero dahil scaled pivoting yung gusto ko malaman sino yung may pinakamalaking leading entry relative to the scale of the respective rows. Okay? So, kunin ko yung 1, 2, 3, 4 just to illustrate yung index kasi ito yung formula. Ito yung pagko-compare natin. RJ, tingnan natin with the tracker, pero wala pa rin naman pinagbago yan. Okay. So, ang gagawin ko ay leading entry ng first row divided by the scale. So, this guy is 3 divided by the scale, so that's 3/4. And then 2 divided by the scale, I'll get 1. 5 divided by the scale, 14. 1 divided by the scale, 1/4. So ito yung scaled leading entries. And the biggest happens at what? The biggest happens at 2. So ibig sabihin, kailangan ko mag-pivot sa second row. Right? Which is different kung partial pivoting. Kung partial pivoting, doon ka sa third row magpipivot. Okay? Pero ngayon, scaled yung ginagawa natin. So that means we must interchange the first and the second row. Kasi sa second row, dapat yung maging pivot. But instead of doing it physically, all right, dun sa matrix, gagawin ko na lamang siya dun sa tracker, dun sa row tracker, okay? So ibig sabihin, dun sa final output, yung first row na ay yung second row nung original matrix. Yung second row dun sa supposedly upper triangular matrix as of now is the first row, and so on. So this indicates na yung upper triangular matrix natin mamaya, dapat yung result galing sa second row yung magiging top row. Okay? Para sa dulo na lang ako magre-rearrange. Okay? Tapos intact pa rin ito. So hindi ko siya pagpapalitin habang ginagawa yung process. Okay? Now, if we do the elimination pass, we will have this. So hindi ko pinerform talaga yung interchange ng rows para makasave ng operation count at saka ng memory. Now ngayon, kailangan natin mag-decide kanino tayo magpipivot among these three elements. But again, okay, supposedly magpipivot tayo saan? Supposedly magpipivot ako ngayon sa third row kasi yun yung may pinakamalaking magnitude. Pero lagi ko yung titingnan against the scale. Alright? So yung R, lagyan yung J, 2, 3, 4 kasi tapos na tayo sa row 1 na alam na natin kung sino dapat yung nasa row 1. Tapos RJ, para malaman ko kung sinong row yung pinag-uusapan ko, para ma-keep track ko. Remember dun sa row tracker natin, ang second entry na sa J equals 2, nandun na si 1. Tapos nandun na si 3, nandun na si 4. So RJ ngayon yung titingnan ko na index. Kasi tapos na yung row 2. Huwag nyo nang pakalaman si row 2 kasi ano na siya, settled na siya to be the top row. Later, siya na yung alam natin na magiging top row dun sa final upper triangular matrix. Alright? So basically, now I'll be comparing the scale for the first row. Si first row, meron siyang 4 dito. Pero ang scale ni first row, ano nga yung scale ni first row? Scale ni first row ay 4. So that means 1 yung scale the leading entry niya. Okay. Dun sa third row naman, 12 nga yung leading entry. Pero ano yung scale sa third row? 14. So that's gonna be 12 over 14. Tapos sa row 4, yung relative leading entry ay 1. So now, palakihan sila ngayon para malaman ko kung sino yung magiging pangalawang pivot. In this particular case, may tie. Tie yung second row at saka yung fourth row. You can decide either of them to be your new pivot, pero para hindi na magkakaroon ng row interchange, dito na ako magpipivot uli kay 1 as a second row. Okay? So dahil ang pivot ko ngayon, ang second pivot ko ay si row 1 mula dun sa original augmented matrix. So walang mababago dun sa row tracker. Kasi alam na natin kanina, naka-place na dun sa second row yung first original row o yung first row dun sa original augmented matrix. So ito yung nagsasabi sa atin ng order doon sa final output. Okay, and then we do the elimination pass. We get this one, okay? Tapos, okay, fix na to. Kasi alam natin ito yung magiging second row. Paano ba siya mas madaling ma-explain? But I hope you're getting yung row tracker, right? Sabi ng row tracker natin, dun sa final output, ang top row dapat natin ay yung row 2. So ibig sabihin, tapos na tayo dito. Hindi ko na yung papakalaman kasi alam ko na sa dulo yan yung magiging top row. Tapos sabi nito, yung second row ng final output dapat ay yung first row ng augmented matrix. So tapos na rin ako dito. Now, nagnalaban na lamang para sa third pivot yung third and fourth rows. So titingnan ko ngayon yung scales. Pero madali na itong makita kasi ito ay nag-zero na. Ang scale ng third row, remember, ay 14. So 0 yung score niya. Okay? Tapos yung leading entry rito ay 3. Divide natin by the scale ng fourth row. 3/4 definitely mananalo yung fourth row. So ibig sabihin yung fourth row ngayon, siya na yung magiging third row dun sa final output. Siya yung magiging pivot dun sa pangatlong pass nung scale nung ating Gaussian elimination, right? So that means, okay, I can perform the EROs, all right, para maging using the fourth row as my pivot. So ito yung magiging final output. Tapos pag nire-arrange natin yan dun sa final upper triangular matrix, ito yung top row. Kasi sabi ng tracker vector natin, yung second row siya yung nasa top. Tapos yung pangalawang row dun sa final output dapat ay siguro gawin ko siyang ganito. Okay. So ito yung magsasabi kung paano natin i-assemble yung upper triangular matrix. So unahin ko raw yung second row. So second row, siya yung magiging top row ng upper triangular matrix. Tapos susunod ay si row 1. Si row 1 daw yung susunod na row. So row 1, you'll go here. Okay. Tapos ang pangatlo daw na row ay si row 4. You go there. Actually, dapat sinama ko pala yung kanilang ano. Sinama ko dapat yung right-hand side nila. Kasi kailangan ko yung right-hand side nila para dun sa back substitution. All right. So let me just transfer that. So this is also hindi na siya kasha. But anyway, I hope you see the process, right? Now, if you do the back substitution, you will get this answers. C1 is 1. Sorry, back substitution nga, no? C4 is -1, C3 is +1, C2 is -1, and C1 is 1. Okay? And then what I want you to do as an exercise, all right, to familiarize yourselves with this process, all right? Pinagawa ko kasi ito kay exercise 6.1 at saka kay 6.2. So gagawin nyo yung without pivoting at saka yung partial pivoting dito sa system na to. And I want you to compare the results that you got from the exact solution, tapos from a rounding arithmetic with partial pivoting and without pivoting, tapos ko-compare nyo siya sa nakuha ko rito sa scaled pivoting. All right? So basically, that's really what I want you to play with. Okay. I'm still thinking if I will ask you to program something like this, or okay lang na mano-mano yung expression natin for now. All right. But let me think about that over the reading break. So sorry guys, I need to lag out right now. So thank you for staying with me. If you have some questions, just let me know via email or via chat, right? Just don't forget, submission mamaya ng IMSP research paper. I need to jump to a meeting. Late na ako ng 1 minute dun sa isa kong meeting. But thank you guys for coming today. Enjoy the break, and let's see each other again after the reading and the Holy Week break. All right, bye guys.
Thank you po, sir.